So this is the title of our talk, Crossing Learning Thresholds um, Progressively via Active Learning. Um, so this is the context for the whole talk. So this is an object-oriented software construction course, and it's a very similar course is taught at two sister institutions, St. Cloud State and Metro State. Both are within the Minnesota State University system. Um, and so one has been taught for 25 years, the other for 17. And the students who come to the class have completed the CS2 course, data structures and algorithms. They're familiar with object-oriented programming, the vocabulary of objects and classes, using libraries, and have worked on some moderately large programs. So as far as we concern, do here our main focus is design, but we have to do some analysis of the things to show how we feed into the design. For instance, we need the analysis to get the conceptual classes, and then in the design we can talk about the software classes and how they get implemented. We do implementation as like a proof of concept for them to see that the design is actually carried through. So the focus is design. So so there are three things that we are talking about today. Use case modeling and FSM modeling. These are kind of combined into one, and some design principles, specifically Liskov substitution principle. And so, um, so let me. So we've been teaching this course for a long time, as we said. So so we assign case study based activities, and when we do that, um, what ends up happening is, students are working in the class. It's an active learning environment, and so I can drop in on their breakout rooms in Zoom, and so I do sometimes overhear their conversation, and so this is the kind of things I hear when the after the topic is presented, like what is he looking for? So they're more looking for what is expected for them to produce, but they're not approaching the situation in terms of, okay, so here's a problem and we have to solve it. How do we go about solving it? So, um, so, so these are some topics that we are focusing on, and we would like to have students show a higher level of understanding and a deeper engagement with the thing. But before we go further, there are some um, questions that so there were there are lots of topics in a course like this, as you can imagine. So the question is, why care about these topics in particular? Um, you know, uh, I mean, in general, there are lots of topics in any course, and we are always have to answer this question: how much attention should we give? So, here is why we are bringing up these topics today, and the whole idea is that these topics can contribute to a greater maturity in the discipline and help them become better as computer scientists or software engineers or whatever they're going to become. Okay, so um, so the importance of modeling. So if we phrase it instead here, um, and students tend to see it as, you know, documentation done after the program was written. And then they had trouble understanding why a certain kind of model was created. So um, addressing these two questions was important, so that when the students go through this activity, they get a feeling that they have learned something important, and that is the notion of being able to model anything that they're faced with. Okay, so this kind of relates to this business of abstraction that was a subject of a talk earlier this morning. Um, and the other thing is, substitutability as a design principle. So of course, we all know that LSP is about behavioral subtyping, and substitutability is not a well-defined term as such. I mean, though there are different notions of it. But overall, what we want to talk about is substitutability as a design principle, and we'll see that um, that also connects to broader issues in the discipline, and that's why um, we care about these topics in particular, because they will give this. So it's when it comes to these kinds of issues as to um, what is important and how we should go about addressing it, is useful to see what is going on in the education literature. And so this uh, so there is a particular concept that's that was it, it was introduced only about 20 years ago, and it has received a lot of attention. It is the notion of threshold concepts. Okay. And so with it is the idea is, in any discipline there are learning thresholds, and so it's something that you get through, and after that you have a different your eyes are opened. I mean, it's almost like abstraction in the previous talk. Understand abstraction, and it's an aha experience. Okay. So it results in a transformed internal view of the subject matter. It's a way of arriving in the discipline. Um, so, what are these? How do we distinguish these? Threshold concepts are transformative. They change the way students look at discipline. They're integrative. They tie together things. They're irreversible. Once they get it, they'll not forget it. They're troublesome for students, and they're often boundary markers um, that are kind of at the limits of the boundary of the discipline itself. And so this is all very nice. So what's the use of doing this? Well, associated with these things in threshold concepts, the next thing that educators tend to do is look for best practices. So these are 5 best practices that have come out over the years after summarized a lot of research. So these are they say distinguish threshold practices and spiral them into your course. Ask students to reflect on this. Okay. And there is some flexibility on how you do your reflection. And then there is, while students are approaching these concepts, there is the notion of the liminal space. The liminal space is where you are uncertain about what it is that you have learned so far. And it's important that they accept the idea of being uncertain so that they don't get frustrated and quit. And then you have to create assignments. And so here, this is very important. This is the key part where, you know, the, these two things here, um, you know, but in the first one, this one up here is where we are actually, um, building the materials needed for the way we teach the course. Okay. So, so this, um, So what can we do with these thresholds? Um, we recognize the important concepts in the discipline. We can identify a specific theme within a course, okay, and then use these best practices. So there's 2 things here. One is recognizing it as a threshold concept that needs to be crossed, and um, then being able to apply those best practices. So, how do we? What we are doing here, to go back to the previous slide, um, we are seeing 2 themes here that we have decided to focus on in this course. One is to grasp the importance of um, um, modeling, and the other one is substitutability as a design principle. Okay, so let's So here are the two things that we have to do. Um, we have to identify the theme, of course, and then create a sequence of activities that should help students connect with the theme. The connection should be fairly obvious to the student. Emphasize the connection with the theme in post discussion, and students should understand why it was done, and so on and so forth. Um, so, so you start with a base level activity that it's very easy for the students to connect with, and then you define objectives and create intermediate level activities, and then define the advanced level activities which not all can attain. Okay, and then there is the notion of reflection on the journey and the threshold that they have crossed. Okay, so this covers um, the basic foundational aspects of what we are trying to do. And so how does all this tie to threshold concepts? Well, if you look at modeling, what we are doing is we are going to abstract away from the specification and capture the requirements in a standard template. And again, substitutability is related to the broader issue of interoperability of modules and reuse. So we are forced to come up with a more abstract characterization of a module's behavior, and that is how we verify that there is substitutability possible. We have to do it in a kind of in an abstract formal way, because we cannot just do it by examples and so on. Okay, and so this is all about abstraction, and abstraction has been universally accepted as a threshold concept. Okay, and there is some literature that points to it. There is some disagreement as to how threshold should be identified and so on and so forth, but the the notion that students need to understand abstraction, and once they grasp abstraction, they've crossed a threshold as far as the computing disciplines are concerned. That is an idea that is accepted. So both of these, modeling and substitutability, are manifestations of abstraction, and so they are valid themes to connect with the threshold concept. And so, what we're going to talk about now is how we used active learning to design all the steps in the process for these two things. So, I'll turn it over to my co-author now to continue the. Uh,
Thank you, Sarnath. Do I just switch to PowerPoint and it will show up, right? Thank you. All right. Let me continue from where Sarnath left off. So, as he mentioned, there are two topics that among the many that we try to teach. One is modeling, the other one is design principles, especially substitutability. So, I'm going to start with modeling here. So, to teach this concept, which we found rather difficult for students to grasp, we do our activities in three stages. One is the initial or base stage, where they get a sense of what modeling is and get an overview of this whole process. They get some examples. And then we take them through an intermediate stage where we have examples of well structured problems, requirements that they are taught in the classroom. They do activities, there is formative assessment, and so on. And then there is mastery, which tests whether students can learn things or do things independently. Our focus is mostly on the base and intermediate stages. The mastery is somewhat beyond the scope of our course. In my university, there is a capstone course where they continue with this process to test the mastery. Now, modeling base level, what do we do? Sometime around the third week of the course or so, we talk about modeling. We talk about the various kinds of models that we can build. So the students are able to appreciate that there are different types of models for different situations, different types of problems, and they are not, or at least most of them are not, or many of them are not quite sure about the right model to choose for a given problem. We give them examples of various situations, various problems at a very high level, and talk about various ways of modeling them. So they do understand the importance of choosing the right model. That is the bottom line here. And they are aware that there are multiple models for the same problem. And for different problems, you might choose something like use case model or a finite state machine model, and so on. Then, after the base level activities, we go on to teach the modeling using case studies. So this is the intermediate level where we essentially have at least two case studies in class. One is using use case model, the other one is using finite state machine modeling. And the requirements are written in a very structured way so that students clearly see how the requirements are incorporated into the model. And we do this for both use case and finite state machine models. So we used an example of a simple library system to teach the use case modeling process. And we have a bunch of requirements that make sense to most students, and they are fairly straightforward, but there may be a couple of tricky business processes that they encounter. And the students are able to see that the model that we build is sufficient to satisfy the functionality that is expected of the system. And one more thing regarding that slide, after we build the model, we go through the design and implementation stages, and they see um, the system in action. And the second modeling is obviously with finite state machines. And this is even more difficult to teach in our experience than use case modeling. And one difficulty that we have had with students is that they have already seen use case modeling and they tend to apply that for any situation. So it needs a little bit of effort to convince them that use case modeling is not always the right option. And to and in teaching this material, we have had other difficulties. Students have difficulty understanding what a state is, and they are also not sure what events are. They confuse between states and events. They don't uh, always recognize the states or events. Sometimes they see the output of the system as a state. So they're quite confused. But so what we do is we As in the use case modeling approach, we have the requirements written in a very structured way that helps them see the states and events more clearly than if it were written in a very loose manner. And we have ways in which each statement in the problem description is translated into a state or a state transition. So here is a concrete example. We teach using this example of a microwave, a very simple microwave with a way to, which has a way to close the door or open the door of the microwave and one button to start cooking. And when you press the cook button, it cooks if the door is closed, obviously, and it cooks for 1 minute. And if you press the cook button again, it adds 1 minute to the cooking process, and so on. And the usual behavior of the microwave, if it is cooking, the light turns on. If you open the door, the light turns on. If you close the door but you are not cooking, then the light is off, etc., etc. So students are confused as to why we can't have these things like pressing the cook button or opening the door cannot be considered use cases. Then we show them the limitations of the use case in an environment like this, in a problem of this kind. And here is how we try approaching this. So we have requirements written like this. When the oven is not in use and the door is closed, the light and the power tube are turned off and the display shows 0 for the cooking time left. This is reasonably precise, and in a real requirements document, maybe things are not as structured as this. And we show them that this can be parsed as the oven is not in use and the door is closed. We have these characteristics associated with that. And we have other types of statements like this, where if the button is pushed when the door is closed and the oven is not operating, then the oven is activated for 1 minute. So we have a situation and we have an action on the part of the user which causes a response from the system that is a state transition. So they are introduced to the notion of states and state transitions here. So this is somewhat similar to looking at the nouns in the use case model and coming up with the conceptual class diagram. That is something that motivated us here. And we have no other kinds of statements in the requirements document here. And students are taught this case study and they were given the, and we teach the design and the implementation. And this is, I think, something new. We haven't seen any approach of this kind in the literature for teaching FSM modeling. Okay, and we have a textbook where we have this in the third edition of our publication. Okay, so it is a Springer textbook, undergraduate text in computer science. And towards the end, we have some reflection on the modeling process, and there is an open-ended activity to express their thoughts on things. Now, let me move on to the next problem, that is teaching substitutability. As we have done for the modeling case, we started with a base level activity and then progressed to more difficult situations. And let me say one thing here. Maybe 3, 4, I don't remember the exact year, 3, 4 years ago, we used to teach the design principles. And when we came to LSP, the Liskov substitution principle, we just taught them the stuff, and from the definition, and students were just blown away by this. It is a very difficult concept for many, if not most people. It's an extremely hard idea to understand. The paper is really difficult to uh, follow. So how do we teach all this? So we decided that we cannot just teach them LSP from the definition or substitutability in general, following that approach. So we motivated this problem using a fairly common example, that of a student, and extending it to cater to graduate students, and then having a common superclass, abstract student with two subclasses, and so on. So this is how we begin substitutability. How do you refactor the situation? Okay. And this is, after talking about substitutability in general, we get to this particular example where we have an example of a class called counter, which increments by one. And we have a client here which does something with this counter, and you can see that it executes a loop that runs for 10 iterations here, assuming that the counter is initialized to 0. Of course, it is initialized to 0 here. You can see for c1.reset, and then as long as the value is not equal to 11, we increment the counter and print the value. This is something that students can easily understand. I mean, every student is able to understand this loop. And then we say, what if we replace counter with something else, counter sub, which increments by 2? And obviously, students can see that this loop is going to not work all that well, because it will never touch the value 11. And so we have an infinite loop here. So students can see that when we replace the reference C1 with a different type of counter, we have an issue. And we can actually create a subclass of counter with counter sub that increments by 2. The students see that we are legitimately subclassing a, or the counter class using counter sub or counter 2 or whatever, but the client didn't function as expected, quote unquote. What is going on here? So in our two universities, when students come to this class, they might have heard about preconditions and postconditions, but they have no clear sense of those concepts. So we do introduce or stress upon the importance of having preconditions and postconditions of the client method. So what is the expectation of this loop? And we talk about postconditions and what is expected of the counter. We talk about preconditions, and then we extend that to the pre and post conditions of the client, of the overridden and overriding methods of the counter class. And then we go on to other slightly more involved examples, set for bag or vice versa, circle for ellipse, that is the famous example from Bob Martin, or Q for bag. And we talk about concepts introduced or dealt with in the LSP paper, things like covariance and contravariance. And we also talk about how things are supported in the Java language for overriding, about contravariance of parameters and covariance of return values and so on. And ultimately, the Liskov substitution principle. And that is what we do in this course for modeling and substitutability. There are other concepts, of course, that we cover, but these are the most challenging ones that we have encountered. So, any questions? Do I close this or do we do? As you wish. Okay. I mean, to show the audience.
All right. Do we have any questions from the audience, from the live audience in Auckland? Anyone online? All right. So we have a question by Dennis. Are you aware of this paper on LSP from Elisa Baniasad, making the Liskov substitution principle happy and sad? That was Splash E 2017.
Uh, Absolutely, we have cited that paper actually in both of Lisa's papers in 2017, and she had one last year also, I believe. So yeah, we have cited both those papers. So here and those are, as I said, that points to um, how important it is. When Liskov's work first came out in '94, I mean, it was given a name and title and recognized in Uppsala and everything. She was a keynote speaker, but it's not come into the common literature very much, and it's still, really shows how difficult it is as a concept. So what we are trying to do here is, it's not just about LSP, but it's generally about the broader notion of why is it that one module can be replaced with another. And that can be interpreted as beyond LSP. It's not just necessarily inheritance or anything. I just got one module, I want to take it out and plug in another module that's supposed to take care of all that. So how does it behave in that way? So yeah, thank you for pointing that out.
All right. Uh, any other questions? Okay, so Dennis, yeah. Any questions from the live audience? I have a question regarding active learning, right? Active learning often emphasizes the social component. People talk about role playing and debating and so on to engage the thinking process. Uh, could you reflect on the social component uh, of active learning in your setting?
Yeah, that's a very good question. Yeah, that's always the challenging aspect of it. But what we have tried to do so far is activities, in the classroom where students are working in groups, so that so each of these things actually turns into activities. So we have a list of activities, that, I mean, if you we can share with those who are interested. And so at various points, a specific activity is given, and then the students work on them, and I, as the instructor, go visit with those groups. They have like 5 to 10 minutes in the classroom, so I visit with them and also in the breakout rooms on Zoom. And then we get back together, and each of them actually says what the contribution was from their group, what was the insights from their group. And uh, and a lot of times, so if those responses in of themselves don't lead us, give us a path to go forward, then we can kind of go back and retune that activity. Yes. So it's yes, so that is an important way we feed into this. And that it's I know it's limited, it's not as vibrant and active, but it's there is a limited amount of scope that we have in here to do this, and yes, so we do try to do that a lot. And it's so we have, like, I mean, right now I've got about 19 or 20 activities throughout the whole semester, and
Mhm.
three of them will connect with the list call with substitutability, and three of them connect with modeling. And they are all come into the course. They play a very useful role in the course as a whole. But at the end, we can, when we do the second activity on substitutability, always connect it back and say, last time we did this and we talked about this. Now what about this? And so there is that maintains a theme through some of these activities, and so we try to connect them. Yeah.
All right. Thank you.
Thank you.